Hello everyone, today we will talk about the medicinal chemistry of antidiarrheals. In fact, I selected only the two common examples. The one is the bismuth subsalicylate and the other one is the opioid receptor agonists such as the loperamide. And as you go through the materials, the only two objectives I want you to pay attention to, of course there are many concepts, but for the sake of reading and preparing for the class and for the exam, I want you to understand how bismuth subsalicylate can form a acylation complex with the tetracycline and why should that be administered with the tetracycline. And the other objective is I want you to think about or find out why loperamide does not have a CNS opioid effect. So apparently, as you will see, loperamide is an opioid receptor that binds to the mu receptors in the intestine and could be used and causes constipation, so it could be used to treat diarrhea. But the nice thing about it is it does not cross the blood-brain barrier. It does not have the CNS opioid effect. Why does it not cross the blood-brain barrier? That's what I want you to find out in today's note. And good luck with that. Thank you. So the first example of the antidiarrheals I'm going to talk about today is the bismuth subsalicylate, also sold under the name cowbictate and peptobismol. In fact, this product has many GI uses, such as antacid, anti-diarrhea, for peptic ulcer. And today I'm just gonna pick, of course, one of the major uses are as anti-diarrhea, and but today I want to mention some of these uses of the bismuth subsalicylate, which is the fact that it coats the ulcer in the GI and thus protect the mucosal membrane from the acid. Bismuth also has an antibacterial activity against the Helicobacter pylori, which is the bacteria responsible for the ulcer. Don't worry about the ulcer for now. We're going to talk about this in later courses. But just for your information, the two major reasons for stomach ulcers is basically the bacteria, Helicobacter pylori, and the use of the non-steroidal anti-inflammatory drugs. As you can see here, the structure for the peptobismol or the bismuth subsalicylate is basically composed of the salicylic acid, which is this part here without the bismuth, okay, and an OH that's attached to the bismuth. So this is the salicylic acid, this is the bismuth, and this is an OH group. And I provided the structure for the acetyl salicylic acid just so you can compare between these two and understand how this product can produce the same effect as the aspirin. So this is the structure of the aspirin. It's also another acetyl salicylic acid. It's also another salicylic acid attached to an acetyl group. So in fact, this acetyl group has been added to the salicylic acid to improve the physical properties of the aspirin, such that it can be more soluble. But the active structure, the active part of the structure is this salicylic acid. So now when the bismuth subsalicylate enters the stomach, it undergoes a rapid dissociation into the bismuth and the salicylic acid. For the bismuth, 99% of it would stay and leave the GI through the stool, and 1% is absorbed and is actually stored in the tissue, in many tissues inside the body, and would have a slow excretion rate. The salicylate or the salicylic acid is absorbed just like in the case of the aspirin. So that's why this product should be avoided in children or at age below 12 years old because of the fact that it's um, related to aspirin. It has the same salicylic acid as the aspirin, um, and as we know, aspirin should not be given to anyone who is less than 12 years old because they can develop Ray's syndrome. Now, in the previous lecture, if you remember, when we spoke about the antacids, we said that any metal that's a multivalent, meaning that any metal that has +2 or +3 or more of these charges could result in inhibiting the absorption of antibiotics such as tetracycline. So in this case here we have the bismuth, which is gonna be dissociating rapidly as soon as it enters the stomach, and it will have this metal, the multivalent metal atom bismuth with +3, and therefore this product, pepto-bismol or cowpectate, should not be co-administered with tetracyclines, for example, because it could actually form this complex, metal chelation complex, and thus it prevents the absorption of tetracycline. If it does prevent its absorption, then the antibiotic is not going to be entering the plasma or the blood, and it's not going to be working as an antimicrobial. So basically it's going to affect its antimicrobial activity. There's one unique thing about the bismuth though. Unlike the other metals we have seen, calcium, aluminum, magnesium, unlike all these metals that we have seen in the antacids, where we had to separate the antibiotic from the antacid by 2 hours. Here, if you take the antibiotic first, then you have to wait for 2 hours before you could administer the bismuth. On the other hand, if you take the bismuth subsalicylate first, then you have to wait 6 hours before you could actually administer the tetracycline. So why is this difference? Why, if we administer the pepto-bismol, we have to wait 6 hours, but if we administer tetracycline first, we have to wait 2 hours? The answer is somewhere here, and that's why I actually provided this piece of information. So think about it, and we'll talk about it in class. The next example of the antidiarrheals I would like to talk about today is the opioid receptor agonists. But before I do that, let me remind you of an exercise that we had in the previous session, such that you could connect this to the previous concepts we learned. And this is going to be this exercise here. So you might remember this exercise when we tried to compare between the codeine, which is in the levo isomer or enantiomer, and the dextromethorphan, which is in the dextro isomer form. We compared between these two, and then we said that in the case of the codeine, it can bind to the mu opioid receptor, and we mentioned that the opioid receptor prefers the levo conformation, prefers this conformation, and therefore the dextromethorphan is not able to bind to the opioid receptor. And we also said that because the codeine in the levo form can bind to the opioid receptor, you will get all these effects, which is painkiller, so it could be used as an analgesic, and there's a potential for abuse because it produces euphoria, and it could suppress the cough, and it causes CNS and respiratory depression. In fact, respiratory depression is the major reason of death for people who abuse such products. And we focused on we spoke about the side effect of the codeine, which is that it causes constipation, and then we recommended that typically these narcotics or opioid receptor analgesics should be combined with something to help for the constipation, such as a stool softener. We're going to link this concept here with today's application. So, but before I do that, let me also remind you that in the case of the dextromethorphan, it was binding to a receptor that was responsible for suppressing the cough, and for that receptor, it didn't matter whether the structure is in its levo or dextro form. So both were actually able to suppress the cough. But because the dextro was not binding to the opioid mu receptor, the dextromethorphan basically did not have any of the opioid-like effects, such as it could not be used as a painkiller, it did not cause any of the CNS depression or constipation. There was some potential for abuse because of the overdose of the dextromethorphan. So, and then of course, in the case of the dextro, we had the dextromethorphan was considered a serotonergic agent. So all this slide actually is just a quick review. This is just optional for you. You could ignore it, you could take it if you like, or you could just skip it. This is just a quick review for your own information. And I wanted to connect this concept to today's concept, which is the use of these opioid drugs as to treat the diarrhea, basically to stop the movement of the intestine. Okay, so back to this slide. After we had this quick review of the opioid receptors, as you can imagine, if we can modify the structure of the narcotics such that they can bind to the opioid receptors in the intestine and stop the diarrhea without having a central effect, that would be ideal for treatment of the diarrhea. And this is what happened here. We have the methadone that was modified to loperamide, which is the drug of choice, which is the drug we're talking about today. And this drug, apparently, as an opioid receptor agonist, it causes constipation, or basically it could be used to stop the movements of the intestine, and can be used for treating diarrhea. And the nice thing about it, that it does not reach into the CNS. It does not have the CNS effect. The question is, how does it not enter the brain, or does not have the opioid CNS opioid effect? And the reason is, although it is sufficiently lipophilic to cross the blood-brain barrier, but this product is basically pumped out of the brain cells through a protein called P-glycoprotein. Okay, so initially the first thing that might come to your mind as why would a drug not cross the blood-brain barrier is that it is not lipophilic enough. But this is not the case with the loperamide. Indeed, loperamide can cross the blood-brain barrier if it wasn't for this pump that actually would basically kick it out of the cell. In fact, this P-glycoprotein is very useful. It's available in many cells, such as in the intestine, in the liver, in the proximal tubule of the kidney, and in the blood-brain barrier cells. Basically, their job is to kick any molecule that they think is harmful to the cell out of the cell. Okay, so before loperamide can actually get absorbed into the blood, the intestine is gonna try to kick it out, and it kicks a lot of the drug. Now, even if it does pass through the intestine into the blood and try to enter the CNS or the brain, the blood-brain barrier cells are gonna, they also have the PGP protein, they're also gonna kick this medication out. Okay, So this is a successful drug that could be used safely, obviously because it's sold over the counter, to treat the diarrhea. Now another drug that has a very similar structure, as you can compare these two, is called diphenhxylate. This is a prescription drug, okay, and it's very similar to the loperamide. It also binds to the opioid receptor and causes constipation. It could be used for diarrhea. The only thing is this drug crosses the blood-brain barrier. Basically, this drug is not recognized by the P-glycoprotein, so it is not being pumped out of the cell. So when we compare between these two, this one here is an opioid receptor and this is an opioid receptor as well. They both could be used to treat diarrhea, okay, but this one here does not cross the blood-brain barrier, does not enter the CNS, it does not have the opioid CNS effect such as euphoria, analgesia, etc., while this one here does. So it makes sense now to have this one controlled and used as an RX-only medication, while this one here, loperamide, can be used as an over-the-counter medication. There is one little piece of information about the diphenhxylate, that it is typically combined with atropine. So think about it, why do they combine atropine with the diphenhxylate as an RX medication? Okay, just something to search and try to find an answer for it if you could, and we'll talk about it in class as well. As I was reviewing the notes, I realized that there was a typo. This should be binding as an agonist. Basically, the drug actually works as an agonist at the opioid receptor, in particular at the mu opioid receptor. Okay, so I corrected this in the notes already, but just in case, if you have read the notes before the voice, you listen to the voice, then it's good to notice that stimulating the receptor is by binding as an agonist, not as an